Welcome everybody. So today we've got I think it is the third masterclass, perhaps, in the Tide series of masterclasses. And we're lucky today to have Professor Thomas Adcock give us a talk on non-linearity in waves in Engineering Guide. So Tom's a professor of engineering science from the University of Oxford. We've been fortunate to collaborate with Tom for over a decade now on a range of different topics. He's been a part of the Offshore Hub, which was the predecessor of Tide, and has also been part of Tide. And he's supervising a number of students actually and research associates now, which originated from UWA. So in thinking about Tide in particular, Eric, who was one of Wenmar's students, and Ian's students looking at wave prediction, is now over working with Tom. And there's also others from UWA as well. So Tom's an expert in statistics and nonlinear physics of extreme waves. He also does wave structure interaction research and has looked a lot into marine renewable energy. He's also doing research into flyaks, which are a type of kayak, which I guess has a hydrofoil, Tom. I think it causes it to fly. Yep. So a number of different things. So definitely reach out to Tom. He's here until Friday this week. So if you're interested in talking to him about anything he talks about today, or just in those research areas more generally, he's happy to talk to you. So Tom's here from Oxford. He's just finished a year as proctor at the University of Oxford, which historically was in the Trinity, one of the three people that would run the University of Oxford. Now it's in the executive, so a senior position. So we're quite lucky to have attracted him over at the end of that, at the start of his sabbatical. So, I'll pass over to Tom to begin the masterclass. Thanks.
Thanks, Scott. I hope microphones and things are working. It's always lovely to be back here to what I certainly regard as my second academic home, hence my background being a fusion of Australia and Oxford. So as Scott says, I've just come from a year of being an administrator. So this is very much sort of my first thing back doing things in terms of talks with waves and things. So I'm probably going to be a bit rusty. That said, I was quite keen and excited to be able to do this, to really sort of try and distill some of what we know about nonlinear physics, but to try and package it in a way that hopefully might be sort of useful for a number of people. And that's not really for necessarily the hydrodynamics specialists, who will probably see that I'm oversimplifying and cutting corners in some of what I say, but to try and present some things which might be useful for people working in offshore engineering, who might be doing model tests, who might be working with metocean people, to give them a bit of insight into not necessarily the details of problems, but what sort of problems we face as metocean engineers. So I'm going to be briefly introducing really why we're interested in sort of some of the nonlinear terms in water waves, and particularly how we end up going about designing offshore structures, just in terms of some very basic sort of statistical things. Then, although I'm going to be talking primarily about where nonlinearity becomes important, I need to start by talking about the linear side, because ultimately that's what we are always building on. And I'm going to really try and cover a bit about bound waves, about the nonlinear evolution of waves, and then about wave breaking. So, although I've been given really far too long of your time to talk to you, there's an awful lot that I won't be able to cover. So I'm not going to really get into anything about wave structure interaction. I'm going to focus on things where the water depth is deep, partly because Jana's here and she knows far too much about shallow water things, and it'd be far too embarrassing for me to venture into such a region. And there are also many bits of nonlinear physics which I find really interesting and maybe really important, like the interaction between very long waves and short waves, which might actually have a very important role in wave breaking. At least that's my view. But there are lots of things I won't be able to get into. But also, those aren't necessarily things that are going to be. They might be very interesting from a technical point of view and might have technical consequences, but I don't think are perhaps something that someone not specializing in metocean necessarily needs to know all about. Originally, when I was planning this sort of talk in my head, I wanted to really cover quite a bit on what's going on beneath the free surface as well, because ultimately, if we're looking at loads on structures, and even more so some of the work that goes on here on loading on pipelines and things, it's what's going on under the surface in terms of the particle motions that's ultimately really important. But I sort of felt I didn't actually opening that can of worms would actually started to get difficult and take too long, and it also started to probably involve more maths than I really wanted to go through here, because the way I'm going to try and do this is to try and skip over a lot of the maths. So although there will be equations, because they to some extent I'll be using them in quite a qualitative way, because what I want to try and give is perhaps more of an insight rather than an in-depth mathematical explanation for what's going on. So I'm deliberately going to be quite lazy about the maths behind things, and partly that's because I don't really want to get bogged down in that, or make people worry if they're not following things. So, as engineers, how do we go about thinking about extremes in the ocean? Well, our standard approach is to think about divide the problem into sort of what we term long-term statistics and short-term statistics. So when we're doing long-term statistics, we usually are thinking about the properties, well, usually of individual storms. How you separate things up into individual storms is a bit of an art, but let's suppose we have individual storms. We know something about their intensity. We can parameterize that in some way, and we can fit some distribution to that based on hindcast data, numerical simulations of weather, etc. And we can do some sort of extreme value analysis, and we can work out how likely all of those things are. But that's really, in fact, in that process, there's very little physics that goes into that. In fact, we're very bad at including physics in that process. And so this talk's really going to be about those short-term statistics. So that within a given storm or within a given hour, when we have some sea state, which will come on to the next slide, what's going on in terms of the waves. So typically we make an assumption that that a sea state, so what's going on in terms of the underlying statistical properties of the waves is stationary, and we need to average that, well, ideally over a shorter period of time, but often over an hour, sometimes even over 3 hours or 6 hours. Now that's really quite a dodgy assumption often, particularly if you're in a cyclone region where the weather can really change very, very rapidly. But we also don't really have much option. So, but let's park that one, because that's not what we're going to be looking at. So let's just make this assumption. We're engineers; we have to make assumptions to go forward. That over some period, we can represent our waves using some that we know the energy falls in some sort of spectrum which might look like this, where we've got this is essentially frequency coming, different wave frequencies coming out here. So we've got some spectral peak, and then we've got some high frequency tail as the frequency gets bigger. Most of the energy is concentrated around one particular direction. That's typically what we get. It's a bit lopsided out here, but so that I know that will often be the case, and that results in some individual waves which will look like this. So one of the things that is going to be important, and I'll try and explain why, is that if we're in deep water, our waves are going to be what we call directionally spread, i.e. they're not going just in one direction. And that, in some instances, is one of the really big differences between the laboratory and the open ocean. We sometimes need to make those approximations, but I'm going to try and explain why you have to be cautious with that. So we've got some sort of steady background, and then we've got these waves on top. And one thing just to note that, so this is just taking that sort of snapshot of waves that we had in the previous slide, and if we look at waves at a particular time, we'll get lots of individual wiggles like this if we're measuring the free surface. This is actually the Draupner wave time series, which is something I studied during my DPhil. You can see that there's one very abnormal wave in there. And one of the things that we're very interested in is how often abnormal waves do occur. Now, one of the things that we again assume, and this is really getting into the statistics, but is sort of going to come back a bit in this talk, is how we actually look at the statistics of each of these wave events. And typically what we are doing is we are saying that each consecutive wave is independent of the previous one. Now, we know this isn't the case, and indeed it's I mean, whilst humans are obviously very good at finding patterns in data which aren't really there, we would expect there to be a correlation if you've got between a big wave and the waves around it. Indeed, we have quite good statistical models for that correlation. But very often we essentially make an assumption which actually turns out to be not nearly as bad as I've made it sound, that we can treat each wave as an independent event, and that enables us to do some statistics on things. So before we start to look at some of the nonlinear physics that really interests me, and hopefully you'll find interesting, let's just talk a bit about linear theory. So the nature of a linear process is that we can simply add up different components. So if we go back to the spectrum we were looking at a few slides ago, each part of that spectrum will be a different component. It will be an individual wiggle, an individual sine wave or cos wave, and we can simply, if we're interested in having a time series, we can simply add up all of those waves, and that will and each one will just contribute to that free surface. And the speed of each of those waves is going to be just down to that component itself. That when we use linear wave theory in deep water, we have a dispersion relation which looks like this. So the dispersion relation relates essentially the length of the wave, although we tend to use the wave number, to the period of the wave, although we tend to use the frequency. And if there's in this, there's no amplitude, there's nothing to mess us up. So each component will be traveling with its own dynamics, and that will depend essentially only on the frequency or on the wave number, which are related through this. So each of those will be traveling with their own speed. So that creates what we call a dispersive environment. So some waves will travel faster than others. They'll come together to form a big wave and then pass through. So if we assume that, then we will typically find that the crests follow Rayleigh distribution. Now, whether they exactly formally do or don't is a slightly mute question. Wave heights certainly don't quite follow a Rayleigh distribution, although it's still very close. But we will see a few graphs which look like this. So, and these are things that we use really quite frequently. So I'm just going to talk through what we have here. So on the y-axis, we've got the probability that for that particular wave, or the probability of a particular wave exceeding a particular height. So, for instance, this is the 10 to the minus 3 level. Level we're often it's sort of the level we're often very interested in. That's very crucial for design. So that's saying essentially every 1 in 1,000 waves, 1 over 10 to the 3, will be bigger than, well, in this case, where we've used a significant wave height to normalize things, that the crest will be sort of 0.85 times the size of the significant wave height. So in a sense, this is trying to sort of establish a linear baseline for our analysis. So let's come on to think about, so that's linear theory, and hopefully many of you have seen that and are familiar with where that comes from. So I decided I wasn't going to go back and recover sort of the physics of that. But I did think I'd try and make the point about what makes waves nonlinear. Well, when we're doing linear theory, we evaluate our boundary conditions at mean water level. So at what on this diagram is z equals 0. And that always seems to me intuitively to be a really terrible approximation, that actually we've got some free surface, which is that we should be evaluating our governing equations on that thing which is going up and down. The reason we can't do that is we don't know where that is before we start the analysis. And I'm always amazed it doesn't make things much worse than they are, that assumption that we actually can just sort of average across all our waves and evaluate our boundary condition there instead. Sorry. So that's one source of nonlinearity. The others come from the fact that our boundary conditions are themselves nonlinear. That when we're doing a linear analysis, we simplify these. But if we take the dynamic boundary condition, which is essentially saying that we've got Bernoulli's equation holds on along a streamline, well, Bernoulli has a nonlinear term in it. And in our kinematic boundary condition, which is saying that the particle stays on the free surface, that also has a nonlinear term in it, which if we want to actually do a fully nonlinear solution, we have to take it into account. Finally, waves sometimes go unstable, and that they break, and that's well, actually my very bad hand-drawn diagram on my iPad probably obscures that, because certainly if you're in Australia, you all know what a breaking wave looks like, and it doesn't really look like this. But waves do sometimes go break, and that's again a cause of nonlinearity. So how would we characterize nonlinearity? Well, in general, we're interested in essentially how much of a departure we have from something which is flat. But we're not just interested in the sort of absolute height of something or the absolute amplitude of something. We're interested in that relative to a wavelength. So you could have a very large wave, but which also had a very, very long wavelength, and that might be very, very well modeled by a linear process. So what we're really going to be interested in is the height, or the ratio of the height to the length of the wave. But for mathematical reasons, rather than using the height, or we could use the amplitude to wavelength, we usually use the wave number times the amplitude. At least that's what I'm going to use here. So that's just rather mathematically more mathematically convenient. Hence, we tend to use that. So as engineers, it's really important we don't get carried away in just trying to tackle problems because they're technically interesting, or because we see a way of resolving some technical ambiguity. It's really important that we only put time into doing a slightly fancier solution, or a slightly more complicated solution, when it's actually going to impact our design. Otherwise, we're putting time where it's not really valuable, and we might be making a process more complicated. As soon as we make a process more complicated, it's easier to make a mistake. It's harder for other people to scrutinize it. So if we can get away with a simpler process, we should. And indeed, there are lots of problems where actually linear representation of the waves is perfectly adequate. And yeah, we might be able to go beyond that, but actually that would be finessing a solution, and there'd be much larger errors coming from other bits of the analysis. And to me, that's not good engineering. That in that situation, you should really focus on the bits of the analysis that are giving you the biggest error. So, for instance, for much of naval architecture, for the design of boats, linear theory really works as well as you need. Most of the error is coming from other parts of the analysis. So for that, you're probably okay most of the time using linear theory. But there are certainly instances where we do need to go beyond that linear theory. So the classic one is essentially the air gap calculation for offshore platforms, where in general you want to design a platform which is higher than the largest wave you're going to get, and non-linearity essentially makes your crests a bit larger. And if you didn't include that wouldn't add up financially, that your structures would fail too often. So we need to include it there. Another example, which is one I've done quite a bit of work on over the last bit, is where resonances with the fluid structure, in terms of the fluid structure interaction, lead to amplification. So I've been mainly working on offshore wind turbines, and those are really quite dynamic structures, and those are designed to have resonances at 2 or 3 times that of the waves that are about to hit them, and that's to avoid the structure vibrating with the frequencies that are about to hit them. But they're often they often don't have much damping. At least certainly the generation of turbines that Ørsted are putting in at the moment, they don't have any sort of artificial damping in them. And if you turn the rotor off, as you need to from time to time, and particularly you want to during a severe storm, then you've got very little damping. So you really care about anything going on at those resonant frequencies. So if you just use a linear model, you basically don't really get much happening, but you might be missing some really crucial loading on your structure. I'm sure there are many more instances, but those are just sort of 2 sort of examples that are sort of important to me. So I'm not going to go too much into the maths of how we analyze waves, but I will sort of touch non-linearity in waves, but I will sort of touch on it. I'm going to start by talking about what I would call weakly nonlinear waves. So in general, we categorize two sorts of nonlinearity. So weak nonlinearity is essentially before the waves break, and strong nonlinearity is after wave breaking. There might be some other strong nonlinear processes, but in general, weak nonlinearity will always be there. That it might be quite small for a wave which isn't very steep, but there'll always be a bit of nonlinear physics, and that sort of ramps up smoothly as the waves get steeper and steeper. Some strong nonlinearity is very different. That's something that essentially is a binary thing. It's on or off. That your waves will behave fine until they get to a certain point when they're too big and they break. So we've sort of got two different categories of nonlinearity, and it's quite helpful to think about those. Weak nonlinearity tends to do things over quite a slow time scale, but it will build up and up. A wave breaking so strong nonlinearity tends to be a very short time scale, but it's sort of a one-off event, and then things go back to normal. So for weakly nonlinear waves, the way we tackle this as standard is to do a perturbation expansion about the mean water level. So what do I mean by that? Well, if we still have this problem that we don't know where the free surface is before we start the analysis. So so that's still a real challenge. So we still want to really use that mean water level. So what we end up having to do is take that mean water level and look at the gradient on that of different parameters on that, and extrapolate those upwards to our free surface, and essentially trying to get as we increase what we call the order of the analysis, we are doing a better and better extrapolation. Now, this technique to some extent is okay. There is though an element that it's really, particularly if we're interested in the kinematics, which I'm not going to cover in detail, but I will just mention here, it really isn't a great way of resolving the kinematics under a very steep wave. That extrapolation really gets quite nasty. Unfortunately, no one's really come up with at least a way that lends itself to simple hand analysis. Clearly, we can do other things on a computer, but particularly for that kinematics, any sort of perturbation expansion is really not a very nice process. Another time when these sort of perturbation methods really break down is for the interaction of long and short waves, where that's just really not the right mathematical framework for tackling things. It's really it is the mathematical framework we tend to use, but it's really not a very good one. So I'm going to talk about sort of different orders of analysis here, and the way we tend to think about this is as we add on another order, we're adding on another term in terms of AK. So if we have a linear wave which has a term A in it, then a second order term will be A times AK, so we get an A squared K term, and if we go to the third order, we'll end up with something with A cubed K squared in it. Now, the theoretical maximum AK you can get is 0.44, at least for a unidirectional wave. But usually actually waves break long before we get to that sort of steepness. So typically the sort of steepnesses we might be interested in are things around 0.35, and if we square that, we're starting to get quite a small number. So we really don't often need to go to fourth and fifth order. Sometimes for certain bits of analysis. People do go further because they can. So sometimes people talk about a fifth order Stokes wave, and for some reason that's become a sort of settled currency. Now that's maybe because you need to go a bit further in terms of calculating the kinematics, but I think often that's going to that fifth order is potentially an example of not great engineering. That fifth order sounds really, really accurate, but actually you're doing that for a very particular contrived scenario, and you can only really do it for that contrived scenario. So having this extremely accurate solution, but for something where there are other errors, isn't necessarily. I think it's perhaps slightly misleading. Okay, so oh, sorry, that went backwards. So I'm first going to talk about what I call bound waves. They might also be called slave harmonics for people with a more mathematical background. So one of the ways in which non-linearity modifies the linear waves is that they're essentially components which don't alter how that wave propagates. So what we have here, and this is going to be a bit of an animation, but we've got this blue wave which has some nominal amplitude of 1 unit, and that's going to be our base wave. That's propagating along nicely in deep water. Now the bound but that wave will generate some bound harmonics. Those come from the non-linearity we looked at earlier, and so that's going to, well, at the second order it might generate some waves which look like this. Now if those have twice the frequency of these waves, so if those were freely propagating waves, those would move with very different dynamics to those bound waves. Those would move at a different speed. But what we end up having is that these waves travel with that fundamental wave, with the thing, and so they don't have their own dynamics. They are purely a function of the background wave of the waves, of the fundamental waves which are actually propagating through. So these will essentially modify the free surface, so that if we looked at what this would look like, and where we've just got second order components, we can simply add these together. So that means that our troughs become a little flatter but not quite as deep, and our crests become a bit larger and a bit steeper, and that's indeed qualitatively what we see in the ocean. So let's think about this in terms of what we call Stokes waves. So what Stokes did back in the 19th century was to try and work through the maths for a regular wave, so for a periodic wave traveling in one direction. He calculated essentially the corrections that you need to satisfy the free surface from a basic wave traveling in one direction. And to the third order, Stokes got something which looks like this. So we have this point, yeah. So we've got some linear term here. So this A is coupled with this traveling wave here. And then we've got something which looks like the thing we saw on the previous slide, where we've got some second order component which is in line, which adds to the crests, and which adds a bit to the crest height and takes away from the troughs, making those troughs flatter. And this is the coefficient Stokes worked out for deep water is this. It's modified slightly as you get into finite depth. And you can extend that on to the third order. So we've got extra components coming in here with coefficient 3/8 at the third order. Sorry, there should be a 3 in that equation. There should be a 3 in here. Apologies that that's got mislaid. So and so that's giving us then higher harmonics, and those continue on. But I've labelled 2 of the coefficients, capital A and capital B, in red, and that's because even for something apparently this simple, where we're just trying to look at a regular wave propagating, when we do the maths, we end up with ambiguities. So one is at essentially the 0 frequency term. So should we, well, on the face of it, we shouldn't have any steady state offset, that we want to conserve mass, and so your steady state should be 0. However, when you try and enforce that, you end up with a steady current underneath, and that's also something we might not really want as in the same way. And indeed, that steady current underneath, that creates ambiguities, because if you've got a steady current, then you have a Bernoulli term on that, and that Bernoulli term reduces the free surface a bit. So you're sort of in a bit of a you end up immediately with a bit of a paradox. Actually, that term doesn't turn out to matter too much from an engineering point of view, which I'll show in the next slide. A bit more of a problem is the one where we have a third order term. So it's third order because it's a cubed k squared, but which occurs at the frequency of the fundamental waves. And to try and get out that coefficient, well, lots of people, I think my student who's currently looking at this has counted 6 different coefficients you can actually put, people have calculated for that term. And very happily, he's got a 7th, which is completely different from numerical experiments, which I don't think anyone's actually managed to extract yet before. But this term is actually reasonably important. So for Hughes' other baby, M4, that M4 is designed to resonate at the fundamental period of the waves, and this nonlinear term is occurring at the same frequency as as the resonant frequency of the M4 wave energy device. So it does matter, and it does actually probably enter our air gap calculation. And so just trying to work through the maths of this is quite challenging. Essentially, everyone makes a slightly different assumption about what you have to do to close out your equations, and that gives you just slightly different results. Some of them can be reconciled, but it's not a completely clear picture. And this should be the simple bit. If we come on to irregular waves, the maths gets a bit more complicated, although, well, maybe I'm being a bit optimistic here. I'm saying that it's better behaved. But in reality, we're interested in what's going on for irregular waves. So in general, at the second order, we want to essentially sum up the interactions between every component that's propagating. So if we go back to our original description of linear waves, there we're just adding up all those different sinusoids. We now want to produce what I'd call the difference term. So the second order term that occurs at the difference of 2 frequencies. We take each component and multiply it by each other component. We have some interaction kernel that we can work out for how those interact, and that occurs at the difference in the frequencies between those 2 waves. And indeed, this is why I said I wasn't too worried about that steady state term, because actually as we start to get lots of components, well, yes, each of these waves will interact with itself, but as we start to add more and more components, that the self-interaction becomes increasingly unimportant. And so as an engineer, I'm completely comfortable ignoring it. Where I'm not comfortable ignoring it is if I'm doing a regular wave test in the laboratory, because then I have no idea what my boundary conditions really are, and I don't really know what to do with it. Although fortunately, measuring a steady state offset is pretty easy to do. So we can essentially do this summation, and it takes a little while, but it's fairly doable. But perhaps the important thing is that this gives us the same sort of qualitative behaviour that we saw before, that our crests become a bit sharper and higher, and our troughs become flatter and less deep, and that for the that's really driven by what I would call the sum term, so the interaction between positive frequencies. So essentially this interaction only with a plus there, so that's very much like that those waves we were seeing before. But the difference term, at least for waves propagating in one direction, gives us a set down. So if we've got this wave group of 3 waves that you can see here at the top, if we look at just what the difference term is doing, ignore these 2 different lines, they're just 2 slightly different models, we actually get a reduction in the water level under that big wave packet. And why do we get that? Well, that's actually one of the few things where I can sort of give a bit of a physical explanation and don't just have to rely on the maths. That if we've got a wave group like this, and so we've got a large wave in the middle of something, that wave is going to be transporting water to the front of the wave group. To conserve mass, we need that's going to sort of pile up water at the front. Water can't pile up, water likes to flow downhill. So that water is going to flow back under our wave group, and that's going to give, and then if we've got water flowing back under our wave group, Bernoulli says we're going to get a reduction in the free surface, and so we see a depression under our large wave group. So that actually reduces the height of our waves. So that's quite good news from an engineering point of view. However, in general, bound waves will increase the height because the second order sum, at least in deep water, is considerably bigger than the difference term. So in general, if we've got this red line, which is our sort of linear model, our Rayleigh distribution, we get this slight increase, and it looks like a slight increase, but it is important when we include second order waves. So this distribution is the Forrestal distribution. It's perhaps not the most elegant one, but that's the one generally used by industry based on some second order numerical simulations. And this does indeed match in general what we see in the field quite well. So although it looks like quite a small difference, this is certainly something that if we weren't accounting for in air gap calculation, we would be getting that badly wrong. So if we can do that to the second order, can we do that to the third order? Well, yes, you can. People have, again, rather than that double summation, you need to do a triple summation to work out the interaction between 3 different components and add those up. And that's fine, you can work through the maths. But one of the problems is that you start to get resonances, or at least the interaction kernel between different coefficients goes to infinity at certain points. And those are a problem, but what actually happens there is you start to get energy transfers, and that's what we're going to look at now. So the next form of weak nonlinearity I'm going to talk about is, well, wave-wave interactions and nonlinear dispersion. Now, these are really intimately connected. Indeed, everything in this, but this talk is intimately connected. But there are some ways where actually these come out of exactly the same mathematical terms, depending on how we write down our equations. So, for instance, I use the nonlinear Schrodinger type equations quite a lot, and in those these are basically all captured by the same terms. However, in terms of trying to give a qualitative understanding, it's probably sensible to separate these out a little bit. So, nonlinear dispersion. So when we were looking at linear waves, we said that these are governed, the way these move across the ocean is governed by the relationship between the frequency of the waves and their wave number. And if you've got that for a wave, that defines its speed, that defines how fast it moves. So if we go back to our Stokes wave, and if we look again at the maths, then, well, we very fortunately don't get any terms with AK in them. So in a second order analysis, that doesn't change how our underlying wave is moving. However, at the third order, we do get a slightly different term. We get this we get this a squared k squared term. So at the third order, we're modifying how fast our wave is traveling, and we're modifying that by something which is third order in steepness. So qualitatively, what this means is that large waves will travel faster than small waves, at least in deep water. So that's something we've deduced from a regular wave, but again, that's something which will be true for a more realistic sea state. So now we have waves moving across the ocean, but not doing so in a purely linear manner. The bigger waves are moving slightly differently to small waves. So this brings us on to the famous Benjamin Fear instability, which is essentially an instability associated with regular waves. So this is to some extent an instability in the same sense that if I try and stand my iPhone on its end, that should be something that I could get to balance perfectly. I can just about do that, but that would be something that would be unstable to any small perturbation in it. That wasn't a big enough perturbation, but maybe I've got a very stable iPhone, but it's already cracked, so I'm not going to push it further. But of course, this is something, going back to sort of undergraduate buckling analysis, this is something you're all sort of familiar with, that things have a stable state, but they can be forced out of them. This phenomena where large waves travel faster than small waves will mean that actually if we try and make just a regular wave train, so if we in deep water, that will become unstable. So let's just try and think through qualitatively why this is. Well, you can, if you're doing a numerical simulation or you're in the laboratory, you can never make a wave which is perfectly the same. Every period is going to be just slightly different, either because of your numerical accuracy, but obviously in the lab, you just can't. Things won't repeat exactly. There'll be a little bit of background sloshing going on. So let's suppose one wave just gets slightly bigger than the wave in front of it. Well, that wave which is a bit bigger, that's going to go a bit faster, and that's going to catch up a little bit with the wave in front of it. And as that catches up, well, that's sort of going to suck a bit more energy in. So that's going to make that wave a little bit bigger again. And then as that process goes on, that's going to get bigger and bigger. And that larger wave is going to go faster and faster until it grows and ultimately breaks, and our analysis falls down. So, I mean, this was discovered by a PhD student who was told by his supervisor to go and make a regular wave, and the student spent a year and a half trying and couldn't, and kept on getting this phenomena. And in the end, the supervisor did the maths and realised that what they were asking was something that couldn't be done. So I thought we'd remove the sound. Maybe we haven't. Apologies for the sound. So this is actually from across the country in Melbourne. So the paddle is producing a regular signal here, and you can see that mostly we've got well-behaved regular waves, but you can sort of see on the horizon that something's gone a bit wrong, that we've obviously maybe the paddle made a wave which was a bit too big, but that's grown as it's propagated down the tank until it makes it's made this wave which is considerably bigger than those around it. So what's the takeaway that you need to have from this? So I've actually been our sort of what seems to be a nice simple base case of just making a regular wave. Well, I've said actually that's a bit more complicated in terms of just bound harmonics than it might seem at first. And it's a bit more complicated because of this. So if you're doing a model test, it might make a lot of sense to run a regular wave. Indeed, it's something I do for particular problems. Sometimes having just one frequency on your structure, that makes analysis easier. But if you're in deep water, and I should stress only if you're in deep water, but often we are, and you're in a long flume and you're trying to do model testing, it might actually be quite hard to make that to avoid this phenomenon, which is going to mess up your nice, well-behaved regular wave. Indeed, my colleague back in Oxford, who is really Professor Richard Wilden, who's not really a waves person, he's at the moment trying to tow a tidal turbine down a 200-meter long tank. The main thing that he's doing in those experiments is he's putting in waves, and this is a very real problem for him in the analysis that he's doing. That as a non-waves person, he just, well, I mean, because he's got lots of frequencies going on, because he's got the frequency at which the turbine's turning, and different frequencies associated with that. So he doesn't want lots of irregular waves which are going to be all over the place and really complicate his analysis. He wants to make a regular wave. That makes perfect sense. That's a very sensible thing to do from an engineering point of view. Let's have one well-defined frequency that you can track through your analysis. But he's run into this problem that because he's in a towing tank, it's a very long facility. So occasionally he gets a completely different wave from this phenomenon to the one that he wants. That's been quite educational for him, and it's been very nice working with him on that. Fortunately, it doesn't mess up things too much, and fortunately, it doesn't actually break his turbine, which would be quite expensive. Now, so this sort of nonlinear dispersion phenomenon is quite important if you're trying to do regular wave tests, which often, as I said, is something we do want to do. Perhaps a more hotly disputed topic is whether this is actually important in the open ocean. And I'm more on the skeptical side as to whether I think it is, but I think I would concede that perhaps there may be some amplification of waves in the open ocean due to this phenomenon. There are certainly particularly some mathematicians who are very convinced that this phenomenon produces all sorts of nasty rogue waves. And there are some engineers who do think that we should include this effect in our analysis. I personally think that that's quite hard, and it's probably quite minor. So but let me just explain very qualitatively why, when we just saw that really dramatic bit of, what's more dramatic than a Lego pirate falling over and capsizing? When we saw what a big wave can do, why do I think that from that nice, well-behaved regular wave, why do I think that's less important in the open ocean? Well, in the open ocean, waves aren't regular and travelling in one direction. Indeed, as we'll see in a few slides' time, the nonlinear physics really forces the waves not to be like that. In fact, and indeed, the bigger the waves get, the more the nonlinear physics forces you to have a spectrum which looks like the one we saw in one of the early slides, where energy is not just going in one direction, and energy is broad banded in terms of the frequencies you get. So in general, the larger the sea state, the more the nonlinear physics forces that there to be an expansion in where the energy is. And so that takes us away from this nice, well-behaved situation where you've got a regular wave and a larger wave can catch up with the one in front of it. And that really inhibits this mechanism from forming in the open ocean. Maybe it does. Maybe there is something there, but it's still, I would say, an open question. And my advice is probably not to include this in design at the moment. People can argue about what's in the field data. I'm very skeptical that we actually see that we can really attribute to this mechanism any extra amplification based on the field data. But there are people who I have a lot of respect for who would certainly nuance that slightly differently. Where nonlinear dispersion does make a difference is actually in the shape of the extreme waves we get in deep water. So these were simulations done 20 years ago now by Paul Taylor, sometime of this parish, and his student Richard Gibbs. So they looked at wave groups, and what they did in deep water, they said, let's start with a wave group which looks like this, which is actually, if you do a linear calculation, the expected shape for what a wave group should look like in deep water. If we've got sort of an average background of waves, what's called the new wave, Richard Gibbs wound that back linearly and then propagated that forward in his numerical simulation using a fully nonlinear solver. And what he found was a wave which looked like this, which looks really, very different to the wave on the other side. That it might not actually be much larger, but it's much broader, and that large wave has moved to the front of the packet. So this might be termed a wall of water, and that's certainly a description that people do use to describe waves in the open ocean. So although this dispersion might not make the waves any larger, it does change the shape, and that might be important for certain situations. So to get that change in shape, there must be a change in the underlying spectrum, and these are what I would term wave-wave interactions. So these are occurring when we sort of talked about that third order calculation where some of those interaction terms were blowing up. Well, what actually happens is that means that you start to get transfers of energy between different components. And this diagram, which is the Phillips diagram, Phillips was an Australian, although went to Cambridge and then onto the US for most of his career. But this diagram, the resonance loop, shows the wave number interactions that will give you energy transfers, that will lead to transfers between some of these components. Now, that figure of 8 loop, whilst quite helpful mathematically, is really hard to understand quantitatively. So perhaps the best qualitative understanding can come from this. So again, this is going back to the beautiful simulations Paul Taylor did 20 years ago, where they started with a Gaussian wave group like the one at the top. And what happened over the course of simulations, the middle one's just a time in the middle and the bottom one's a time at the end, is, well, what are the changes? Well, the biggest change is perhaps one which is the least obvious, but the peak of the spectrum was initially here, and that's been downshifted. So what has happened is that those resonant nonlinear interactions well, that's led to the peak of our wave spectrum moving downwards. So this very much does happen in the open ocean. That this is why when wind first generates waves, you get quite high frequencies, and over time the nonlinear interactions move those move the peak of the spectrum, so you get longer and longer waves, and eventually sort of get the waves you see in the Southern Ocean, very long period waves. The other interaction which very much interests me is that you get energy spat out at 35 degrees to the direction that the waves are going in, and indeed these energy transfers go to high frequencies. So you start to get a high frequency tail forming in terms of what's happening, although actually these waves are propagating really in a slightly different direction. But this is why I said earlier that I'm quite that we don't get regular unidirectional waves in the open ocean. That this is, although this is a weak nonlinear effect, this occurs quite slowly over time. The larger the waves, this is a very nonlinear effect, so the faster it will happen. And so if you try and make a very large regular wave, over time this will start to broaden as this spectrum broadens, shed energy to make it more directionally spread, and that will really inhibit this Benjamin Fear mechanism from kicking off in the open ocean. So that's at least that's my view. So I've already spoken a bit about this, but I really want to make a point about the difference between unidirectional and directionally spread waves. So the examples you've just seen, those were all for directionally spread waves, and that's not because so making waves directionally spread, that makes things a lot more complicated. It's much harder to do analytically, numerically, and certainly experimentally. And I was preaching earlier that I really didn't want to add in unnecessary complication to a problem. So why was I showing directionally spread waves? Well, in the real ocean, if you go a bit offshore, the waves are directionally spread. You don't have infinitely long crests. There's always some degree of directional spreading. Indeed, it's unstable for it to remain in a regular form. And this is really well, let's go to the bottom bullet point. So why does this lead to differences in your in terms of the extremes you get in a unidirectional waves to directionally spread ones? Well, in one reason, and I think these are two separate reasons. I've never quite been able to reconcile them into one. But one reason is that if we think about that Phillips diagram, which I know was sort of quite hard to understand when you haven't seen it before, but you can see here that this wave number is going at a different direction, and this one's going in another direction again. If we only have unidirectional waves, we're just confined to interactions along this line here. So that immediately says that that the nonlinear interactions you're getting are really quite different in a unidirectional wave compared to a directional sea state. So, and that's going to be important when a large wave forms, because, or if we're interested in the non-linearity of a large wave forming. The other reason perhaps is even more important though. So what I'm showing here is, well, we'll work backwards. At this point, we've got a perfectly focused wave group, and for this example, I've decided we're ignoring all the non-linearity, because the non-linearity is going to be the thing that we're sort of adding on top of the linear analysis. So, And let's say like Paul Taylor was analysing in those previous figures, we've got the average shape of an extreme wave event at some time t. Well, we can look back just using linear evolution at what happened at how that wave group forms, how that disperses. I mean, and because it's linear, we could go forward or back in time. They're identical. But let's go back in time. So let's trace this wave group back over time, and let's pick off the largest point in that wave group. And here I've only gone back 5 periods. Now, what's happened with this line? So this line is our directionally spread wave group. So in this case, we've got waves which were, well, from this point, coming in from all directions to form this extreme event. And so we've actually lost quite a bit in just 5 periods. We've lost quite a bit of amplitude, and that's going to continue to tail down. However, this solid line, this is for a perfectly unidirectional wave group. And what we can see is that if this had the maximum amplitude at that perfect focus point was 1 here, well, 5 periods before, that's barely any smaller. So that group is still very, very nonlinear. Now, remember that the nonlinearity we're really dealing with here is a cubic nonlinearity. So we really want to, we want to be, arguably squaring this, but maybe cubing this to tell us how important the nonlinear interactions are. But what we can see is that essentially the solid line, that the waves remain, just on a linear basis, remain much, much larger for much longer. So there's a much longer time for those nonlinear processes to get going and to do something interesting and potentially make more rogue waves than we get in a directionally spread C state. In a directionally spread C state, waves sort of come in, form a large event, and then spread out again, and that's a much faster process. So that's deliberately a bit hand wavy, but what this really means is that the formation of a large wave event, if we're interested in the nonlinear physics of it, is really quite different in a directional C state compared to a unidirectional one. So what should be the takeaway from that? Well, one is that you should be, let's say, if we're dealing with a deep water problem, you should be very cautious of anyone who says, who's either done some analysis, however they've done it, and they've found lots of what they would call rogue waves, lots of additional extreme waves from a unidirectional analysis. That's probably not going to be representative of what happens in the real ocean. But sometimes we have to make unidirectional waves. Let's say we're in the laboratory, and most places, and sometimes just for practical reasons, we have to make unidirectional waves because that's easier, or we've only got a flume. Basins are very expensive and difficult to make, so we're having to make unidirectional waves, and we want to make random waves, but we want to do some model testing because we need to. So we have to be pragmatic. We have to do that as engineers, but we also have to be very careful that we should be aware that we're probably that if we try and make a random wave signal, if that has some nice realistic spectrum when we input it, that's going to be we're probably going to get more large waves than we would in the open ocean at our sample point. And we might not be able to do anything about that, but we just need to be aware of that maybe if we're just taking our loads, let's say we're taking the response off directly, we might be overestimating our loads quite considerably. So just something we need to work around from an engineering point of view. Okay, so I've gone through what I would term weakly nonlinear waves. We're now going to briefly look at what I would term strong nonlinear wave interactions, and in particular wave breaking. So the steepness of a wave is limited by what wave breaking. Qualitatively, essentially, at some stage in deep water, if the particles within the wave are going a bit faster than the wave itself, that wave can't be stable. So for that Stokes wave, for that regular wave, we get a limiting steepness, but in practice, things tend to kick in at a much lower steepness. And we've got lots of different criteria that people have come up with, some about the geometry of the wave, some based on the dynamics of what's going on, and some on the kinematics of what's going on under the wave. Probably certainly the last two are going to be the best, but they usually involve having to have some knowledge of what's going on under the surface in terms of the kinematics, which is difficult. At present, we tend to assume that if the velocity of the horizontal velocity under of the particles is or that divided by the speed of the wave itself is greater than 0.85, that means our wave is going to break. That seems to be a pretty robust criterion, but still most of the work has gone on in unidirectional waves. I wouldn't expect that to be very different in directional waves, but it will certainly be a little bit different. So we still struggle really to know when wave breaking will happen and to really model it well. Certainly trying to understand the full process of what's going on when waves break remains very much an open question. It's a horrible multi-scale problem. What impact does this have on our distribution of well, in this case I'm looking at wave height rather than crests, but of the size of our different waves, going back to our probability of exceedance plots? Well, what we tend to see is that this will tend to sort of drag down the size of the largest waves. That essentially, because the waves which without wave breaking would come down here, those are being the size of the largest waves is being suppressed. So that's potentially quite good for our analysis. Well, maybe we care if we've got waves actually breaking on our structure. That can give us quite large local loads. But if we're just interested in the air gap, trying to get our structure higher than the waves, well, this can be quite helpful. And it probably is one of the main reasons why many offshore designs are quite conservative, partly because we don't understand breaking waves brilliantly, we really want to be quite cautious about how we include the effect of breaking waves in models. That said, from my brief forays into industry practice, I've certainly seen structures designed for waves which just couldn't exist because that wave would have broken, and that seems too conservative. So I quite like what the Imperial College models that my friend Yanis is developing at the moment for that limiting wave height, but I still think there's lots of scope for including at least a bit more physics in that analysis. Okay, so I'm going to spend the last few minutes of my talk trying to sort of get a bit more perhaps philosophical and talk about why it's so hard to analyze all the non-linearity in a completely satisfactory way. So when we try and tackle things as engineers, well, we could do things analytically, but as I kind of showed, even when we go try and do even a simple, well-behaved regular wave analytically, we immediately start to get into ambiguities. So let's not go too far down that route, and let's focus on, well, physical experiments, numerical simulations, and field data. Now, so why is it so hard for us to get to actually include the effects of nonlinearity perfectly in each of these? Well, in all of those cases, it's really quite one sort of overarching thing is it's very hard to get the exact environment that one wants. That if you make waves with a particular characteristic, those waves tend to change due to the nonlinear physics. So then, have you really got the conditions you want? But let's look in a bit more detail at each of these. So what do we really want to do in the laboratory? That clearly the laboratories, these are pretty good for most things, because most things we're doing in waves don't have big Reynolds number effects. Surface tension is usually not a big issue. So we've only got fluid scaling, and fluid scaling really works pretty well in the laboratory. So ideally, if we want to test a structure or do some analysis, we need a basin rather than a flume. But that's quite difficult, because that's basically because basins need to be really big, and if they're really big, they need to be really they're going to be really expensive, and they're going to be expensive not just to make, but also expensive to run. Now, and even worse is going to be trying to include currents in them. That one thing I haven't spoken about in this talk is the influence of current, which is quite important on many of these things. But if we want to, whilst putting in some current to a flume is kind of okay, putting into currents in a big basin, well, I'm certainly recall when Shanghai Jiaotong opened their big basin 15 years ago, and they turned on currents, and they took away power from 300,000 homes across Shanghai because they hadn't done the calculation properly, and you need some really, really big motors to move an awful lot of water in a basin. So you're not really going to be able to do currents, or that's going to be really, really expensive. And also if you've got a basin, it just takes a lot of time to settle down. So, but ideally you want a basin, because we don't want those issues with unidirectional waves that I spoke about earlier. So you do want to pay for a basin, but this size problem becomes a real issue, because this is the Imperial College Basin, and which I think, although it's very small because it's in South Kensington, one of the most expensive places in the world. South Kensington's a bit of London. It's a very good quality basin, but I have a big criticism of it, which is that you're making waves with these paddles here, and you're doing your test. Well, you don't want to do your test too close to the bit where you're trying to absorb the waves. So you have to do your test about here. So you're sort of 1, 2, 3 and a bit wavelengths away from where you've made the waves. Well, that's actually not very far. That if we're interested in how some of these non-linearities develop, they need a lot more than 3 wavelengths in order to develop properly, in order to sort themselves out. Particularly because very close to the paddle, you've got all sorts of nasty things going on. So you might not really be getting really the right distribution of waves, because you're still, shall we say, really influenced by what you're putting in at the paddle. Your waves just haven't had enough time to evolve into what I would call a nice, well-behaved equilibrium state. Not much we can do about that, because we just can't really build a wave basin big enough. It's just not practical to be very long as well as very wide. And we also do still have some scaling issues, particularly if you're interested in breaking waves. That breaking waves just look just to the eye, look very different in the lab compared to in the field. That's often very much because of the air entrapment and the aeration within the waves, but that does then actually have an impact in what's going on in terms of some of the loading issues. So we have problems. The laboratory, clearly very important, but has challenges. So why can't we just simulate everything on a computer? So We've got very good at simulating non-breaking waves in deep water. It might be quite computationally demanding to do that well, but it's certainly possible. And yes, we'll have the same problem that if we're very close to where we're making waves, we're going to be still be very influenced by the imperfect way in which we're making the waves. But we can run a very big simulation that just needs a bigger computer and more time. So we can potentially get round those problems with sort of the artificial way we have to make waves. But we do then run into issues when we actually, well, one issue is that if we want to run those simulations, if we want to do these at any scale, we need to essentially assume the flow, a potential flow type model, and we need to discretize it in ultimately a way that's much coarser than the sort of very small scale behavior you get through wave breaking. Plus, wave breaking, as soon as the wave jet hits the water in front of it, that's going to create effects which clearly cannot be captured in a potential flow type model. So we have a problem when it comes to wave breaking, and if we're trying to make a random waves in a large sea state, wave breaking is going to be important as a limiting effect, as something which changes the spectrum that's going on. We can try and hack that, but we can't really. But we have issues doing it. Plus, if we're ultimately, most of the time, we really want to put a structure in this. We want to actually test what's going on in terms of loads. That's often what we're doing in the laboratory, that we're sticking in some structure. We want to analyze how it responds to those waves. Well, again, that wave structure interaction is probably not something we can capture with the same model that we're using to run our random waves across our ocean. There's going to be lots of different physics involved that we want to capture. So numerical simulations also have some very severe challenges. So finally, what about field data? Well, this to some extent should be the gold standard, and it's clearly going to be important to do what Hugh's doing with M4 at the moment, which we very rarely do, is to actually analyze what happens in the field. But it's difficult, and it's also expensive. But we can't really do this for new structures if we want to test and iterate on design. But perhaps most of all, and perhaps why it's so difficult to really understand things perfectly from a theoretical point of view, we can't control the conditions. Very often we can see that our assumption that the background sea state remains stationary over an hour isn't a great one, but we may not get the exact conditions that occur. Let's say we put something out for a particular winter or summer, and we might not get the exact sea state that's the one we're really interested in, or the really nasty sea states, they've got some complication. So, or there's a big current going on, or there's some big complicating factor. So field data also has its issues. So perhaps my takeaway from this is that whatever we do, we have challenges, and that's obviously great news for us as engineers, because it means that our expertise counts for something, that we need to use a combination of different methods and our intuition about the problem to really try and identify for a particular problem what are the important bits of nonlinear physics that we really need to capture, and what's the best way of not maybe getting that perfectly, but capturing that to some degree in our design. But there are certainly situations where we really want to care about the nonlinear physics of waves. Then this is obviously a particular bug of mine, but I will come back to it. we do need to be careful when we're doing things in the laboratory where we can't make the same sort of wave conditions you might have in the open ocean, and that unidirectional waves have their challenges. Particularly regular waves are even more challenging in terms of things which don't always quite go right. And engineers, our job is to really think about what's going to be particularly important for a particular design, find a way of analysing that, of understanding that, making sure that doesn't mess up something else in our analysis, and then using our judgment and maybe saying, actually, we can't analyse that, or that's just too great an uncertainty, therefore I need to apply a bit of safety, factor here, that's going to ultimately be the most cost-effective way of dealing with something, or make the case that you do need to do more in-depth analysis, but try and do the right test that doesn't cause more problems. So ultimately, engineering judgment is really very important, and we can't just rely on maths. So I hope I've tried to sort of give an insight into some sort of bits of how wave non-linearity does actually impact what you might be doing in terms of practical offshore design. I hope I've struck a bit of a balance between the mathematics and what we sort of need to take away qualitatively, and that you've had a bit of an insight into at least how, if nothing else, how metocean engineers go about thinking about nonlinearity. So with that, I'm very happy to show off my prowess at using ChatGPT to make random images. And thank you all. I'm very happy to take any questions or clarify any points. So thank you.
I'm curious about the directional spreading. So you talked about directional spreading mainly in the context of sort of Paul's work and how it results from the energy transfers. But obviously in the ocean, you have directional spreading that results from the fact that the wind doesn't blow constantly from the same direction. So in the extreme waves, do you think that the fact that you actually in the real ocean have more directional spreading, do you think that further suppresses the likelihood of extreme waves, or does it maybe increase it because you have more chances at constructive interactions?
Well, I mean, for a given average property, you have less chance of, you probably have the same. You formally have the same chance. So yes, and there are lots of reasons why, if you're in the middle of the ocean, you don't have a unidirectional wave, and indeed that's partly your wind input isn't uniform. But even if it were, that would be unstable. And of course, winds will always be changing slightly their direction. And of course, wave breaking, which is always going on to some extent, that's also going to lead to some directional changes. So there are lots of reasons why we get a directional distribution of energy. I am still very interested, going back to my Draupner work, which is where I started, in situations where the wind's going in a very, very different direction, where you've got very big distributions of energy, but I didn't really cover that there, because then the interactions are much larger. But I just don't think you can get some swells can have quite small distributions, but then they've just, by definition, they've got quite small, they're pretty linear. So there's sort of this feedback, which there's lots of, as you try and make the waves larger, that probably means you've got a very, very strong wind. So any small changes really affects things more. So I just think there's this, I've never really been able to write it in a articulated in a way I could in a scientific paper, but there's very much this feedback which really forces waves to be directional in the open ocean as they come into the near shore of other physics takes over. Yeah, in deep water, I think it would be it is something I would like to try and do something to try and maybe do a counterfactual, try and really think about how we could make a regular a unidirectional wave in deep water, and try and work back from that to look at all the challenges that would have to, and all the massively improbable things that would have to happen for the way mathematicians like to think about waves to really come to pass. Thank you.
First, and I guess the two questions here. Is there a rule of thumb that you have for one of the openings that ideally see between the paddles and the structural and measurement one? And I guess the validate that, have you looked at measuring that for a surface at your site to confirm you're going to be steep or steep on one analyze?
So I don't think there's I don't think there's a good rule of thumb for how long you should wait, or how many wait, because it would be, in a sense, it would be. I mean, I can think of some ways how. I mean, you could. Someone at Georgia Tech has a nice theoretical curve for how waves evolve as they move away from the seas, and you could use that to try and come up with some sort of length scale. But I actually think that would probably be, from a practical engineering point of view, that would be the wrong way of thinking about things, because it's just so expensive to make a large basin that you kind of have to work with what you've got. You could do that, and much more for if you're in a wave flume, where you do sort of get slightly similar effects, but they end up with something which is not physically what you get in the real ocean. So I mean, I think you would need such a large basin, and you probably ideally want sort of 10-15 type periods, which I don't think they're really basins that you can really make them wide enough to practically do that. You could have a go, and it is something I've actually thought about doing numerically, sort of to try and answer that question, where obviously we can just make things larger and see. But I think ultimately it comes down to more the engineering judgment. I think the other thing that's sort of, to come back to your how do you know what waves you're really getting? Well, obviously you can measure things in the laboratory, and that's fine. You can measure your free surface, and you can probably even measure the directional spreading if you're suitably gauged up. So this leads to a really interesting question as to what you should be looking for there. So I think my colleagues down the road from me in Oxford at Imperial, what their philosophy is, the sea that you make at the paddle, the sea state you want, and then there'll be some non-linear interactions, and those will have happened. As I said, I think they're still happening. They say they will have happened, but I think they're very, very clearly still happening at the point they're interested in measuring. But they'll have happened, and therefore, actually, if you're sort of putting in what you think is your design sea state, that's then been modified in a realistic way. But that seems a bit strange, because those modifications, I mean, and I in a sense that's wrong, but all answers are wrong. That if you actually want to make waves with a particular spectrum at a particular point, well, you can do that by trying to sort of iterate and correct your input signal a bit, but then maybe you're actually then not capturing some of the real non-linearity you're interested in. So there's I think a real dilemma here. And if I wanted to be ambitious and think about how one might get around some of this, is trying to be a lot cleverer about how we actually make waves. That at the moment, all we do if we're trying to make a random signal is to essentially move that paddle, and if you're doing things and you might be able to correct that to the second order, particularly for the sum waves, potentially even go higher. So but your underlying signal is still going to be one where your waves essentially have no correlation between each component. Now, maybe there should be, maybe in the open ocean there are really some correlations. They might be weak, but some correlations, and maybe that is something that one could think about trying to program in, and that would lead to actually making waves in a much closer to equilibrium sea state. That's something I've sort of considered as an ambitious project, and I hope someone, but it's quite ambitious, so I hope someone much cleverer than me takes that up and finds a good way of doing it, because it might be something that helps, although it's also quite abstract, and I think it's important, and I think it is some non-linearity that's important, but it might also be quite hard to persuade people to really do that. It's hard enough to persuade people to make waves using second order generation, let alone, which we can do, which is and we really should be doing, let alone some of these, well, even higher order non-linearities.
You had the Paul Taylor's new wave up, and then kind of what it might look like evolved, counting for the traditional non-linearities, and you get that kind of wall of water.
Yeah.
I'm curious. So the new wave, like say Dropner, like lines up quite well, that shape. So why is that kind of wall of water? Why was that not observed instead of?
Well, the Dropner is an interesting case. Well, firstly, I would say when the evidence we have is that does happen in the open ocean in general. And it's quite hard to distinguish, to actually measure we're quite good at measuring the average directional properties of waves. We're not great at measuring the very local directional properties of waves in the open ocean, other than by eye when we do it really, really easily, which is quite interesting. But we certainly we do see a tendency for the large wave to move to the front of the wave group, exactly as we would expect that the large wave's traveling a bit faster, it should move to the front of the wave group. And that is something that you can see and find. It's a bit blurred because you've got statistical variation, but you do find that in the open ocean. The Draupner event, well, we don't know exactly what happened, and we certainly don't know exactly what happened directionally. My hypothesis, which I came up with many years ago, but which well, has now been described as a consensus. Which is which I think has now become a consensus. Other people have used that word to describe it. Was that the Draupner event was this strange event where not all the waves were going in one direction. Some of the waves were going one way, but a smaller packet was going in another direction. And there's a lot of circumstantial evidence, which I really worked through back in the day when I was a graduate student, which supports that hypothesis, and I think that is now accepted, but we will never know. But whilst obviously Paul saying was for a nice deterministic wave group on average, we'll always see a bit of statistical variation. But I would be very surprised if and probably when we are able to measure extreme waves in the open ocean. I'm very excited by, I should say, the latest data coming from the SWAT satellite in terms of that we might be able to actually measure rogue waves from space for the first time. which is something I would say you need to be very cautious about doing. I'm sure lots of people will publish papers in very fancy journals which turn out to be noise rather than rogue waves from that data set. But that is the first time from satellite data we've actually been able to really get an accurate picture of the free surface of the ocean, or at least in a way that's even remotely accurate enough to do things on an individual wave by wave basis. And I would really hope that in that data set, if we're really careful about analysing it and know what we're looking for, we would be able to see essentially those walls of water forming, because they're quite, I mean, they're in terms of the width of the crest, you're increasing by, well, in pool simulations, a factor of 3. Maybe now adding a bit of statistical variability might be a bit less than that, but that's a pretty dramatic thing that I hope in the next few years, when we've really got to grips with some of the SWOT data and seen a few nice well-behaved North Sea storms. Well-behaved, I mean all the energy going in one direction, not some horrid cyclone. We might well be able to see that, and I don't think it will actually matter much from an engineering point of view, but I'll certainly be really excited from a technical point of view if we're able to do that.
So in different kind of applications, such as the perspective for high order noise or the dimension in some data, for different applications such as for safety analysis, we're making us a bigger linear figures in that, considering high order errors. But for different other applications, maybe the error gap dimension or factorings or wave interaction. There are many or high order importance of the high order effects and maybe is different. Such as maybe the water property management stages for the experiment in block part around the proteins as well. We found like the second order components contribute around maybe 20% of that. So in terms of that, we know that okay, the engineering design, we need to consider that part to have the accuracy. At the same time, also we are curious that is there any maybe more different kind of applications, such as even higher order component, like over 4 order, would be more important, or even more important than the second order one. Do you have any experience for application knowledge of that? Because I'm not knowing, especially when you involve in like a mixed structure traction problem, maybe you might come also from the system itself or other sources, energy. Importance greater changes. Are there any some kind of experience about some applications here?
I mean, I think any dynamic system you can have a whole range of where an interesting resonance might fall, and the waves you get in nature will also have a variety of frequencies, and so you could start to get you could have interesting resonances going above the third order. Certainly for some floating things, I'm sure that's the case. That said, you are starting to potentially get into quite small waves, and so it then but absolutely I think this is where perhaps it is very hard to generalize, and something in the talk I had to generalize, but this is where we pay engineers to have judgment and not just follow things blindly. And if there is something interesting at a particular order, then in a particular frequency band, then you want to think very carefully about what things could be exciting things in that frequency band, I guess. And that's you shouldn't just sort of think, well, my waves are definitely here, therefore I should ignore it. You need to think about what different things could actually end up exciting sort of such things.
Just last week on. So You talk about the limiting sequence before breaking, like 4-4. In a directionally spread sea, can you go higher and not break?
There's a Nature paper that a good friend of mine wrote, where essentially they were looking at waves coming from very directionally spread, and you certainly can go higher. That said, one bit of work I'm planning to do with yet another Australian, my colleague Professor Mostert in Oxford, is to really try and look at this for perhaps more less extreme directional cases. But indeed, coming back to the Draupner wave that was asked about earlier, that one of the reasons why we think that was so directionally spread was that actually when we try and make that wave where most of the energy is going in one direction, we just can't make a wave with that particular characteristics. It just always is breaking. Now maybe it was slightly breaking in the field, and it's really hard to tell whether a wave's breaking from a simple time series. But that's one of the reasons why we just can't make a wave that big with most of the energy going in one direction. But I am quite interested in seeing whether we can push that limit, and that's something I'm hoping to do with Wouter Mostert over the next few years to try and look into that. But yeah, waves can get bigger, but by that stage there's probably lots of other interesting things going on as well. So he is finding much bigger coefficients than you would expect, and much larger positive coefficients than you would expect. Paul and I have some skepticism over a value. So I think it's 3/5, or it might be 5/8. I can't remember. But also Paul and I can't find anything wrong in what he's done. So and it seems to consistently check out, which is really strange. But it doesn't fit, and is so I'm not. I think it's publishable because it's interesting, but I also wish we had at least some stronger theoretical basis for it. But Paul spent about 2 hours trying to find something wrong in what he'd done and failed. So I'm feeling moderately confident in that at least we're not doing anything completely stupid. But it's quite hard to separate it out because it's occurring at the same as you know, but at the same frequency as the fundamentals, and it's really tricky to actually extract that. I know you guys have been trying in a slightly different way to us to do that, but it's hard.
Just one more question. No. Okay, well, thanks very much, Tom, for